Okay, dear reader, it's time to trust me now and get yourself a graduate Statistical Mechanics textbook. This is a new one. It's fantastic. There are a whole bunch of really good ones that have been published throughout the years. Recommendation is one of these or something close to it. And why do we have to do this? Well, in the end, like we mentioned, humans, we understand pressure. We don't actually understand temperature, although, however, we have an idea of equilibrium. And so the world of statistical mechanics actually is taught in the realm of physics. Now, I'm not going to go all the way down to the very, very bottom. So a pure physics textbook might start down at the level of quantum mechanics and then build up fermions and states and all this. And so as you're reading, do feel free to gloss over some of these things that are sort of them counting the total number of states. But ultimately where we can start in and where we can hook in is that you have a system, and the system has an energy, total energy, capital E, which is the sum of the number of molecules that have energy little e, and you're adding all of that up, right? And clearly you have some total sum of n molecules. Okay, so this is the start of it. Now, those molecules, you can imagine them being a configuration just banging around. They could be in any sort of configuration. And the interesting measure here is how many different configurations can they be in. Now, at the macro level, so we would call this macro state, right? We only might know the total number of molecules. We might know the volume of the space that's occupied in, and we might know the total energy. That would be it. That would fully define our microstate. Now, we'll be able to delve things further here, you'll see here in a second. But at the microstate level, so for instance, as an example, if I had, let's see, two boxes. In this box I had molecule A and I had molecule B. And in this box, let's just have four of them. So C, D, E, F. And I'm going to do this really, really silly and just say that kind of binary form, A can have an energy of 1 or 0, B can have energy 1 or 0, likewise. And so if I was writing down the total number of combinations of A, so what are the total combinations of A? I could have 0, 1, or 1, 0, or 0, 1. That would be the total combinations, just kind of representing a list. So here I have two combinations. I have two particles. They only each have two energy states. I'm calling them 0 and 1 because why not? It's just a name, is not necessarily the energy value. I can associate the energy value with it and then add it up if you like, but I'm just talking about the total number of configurations. Now over here, you have 4. And so I could have, in fact, over here I better mention that since they're not unique, let's say I can actually have 4, 0, 0, and 1, 1. So over here, I could have 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, dot, dot, dot. You see all that? All the way to 1, 1, 1, 1. And so, all right, that's the total number of combinations I could have. Now, if I merge these two together and then get rid of this dividing line, and I now have 6, then honestly, it doesn't take you long to then realize I can now add these numbers, maybe in a different color to the side, but it's multiplicative. And so it's really, they would say it's the total combinations of side 1 and the total combinations of side 2, such that the total configuration of the whole thing would be psi 1 times psi 2. Or sorry, omega 1 times omega 2. So this is all possible microstates. Now, what's really happening here is each one of these is really only a function of energy 1. So some energy level will give a distribution, and the distribution again is going to be down kind of in the world of quantum mechanics. We don't have to understand for our purposes, what's the distribution? It's just, given an energy, there are this many possible states of the distribution, and then in state 2, and the system has energy 2, there are, again, this many distributions. And so the total sum is going to be each this multiplied by each other. Now, I also happen to know that if I'm going to call, let's call E0 the total energy of the system, which is E1 plus E2, then I can also come down here and rewrite this E2 such that this is system 1 energy 1 and system 2 at the total energy minus energy 1. So honestly, they're both just a function of energy 1. So the equilibrium state, over here, the equilibrium state is going to be the state for which I vary the total number of possibilities compared to E1 is equal to 0. So let's do that. I can do that by chain rule. And so that is the derivative of state 1 with respect to E1, and then times E2 of, I'll just go and put E2 in there. And then I have state 1, E1, the derivative of state 2, well, it's actually only a function of E2. And so then I better take the derivative of E2 with respect to E1, and that's equal to 0. Now, I have a formula for this. What is it? It's actually over here. So in fact, I can say, well, gosh, what is E2? Well, E2 is just total energy minus E1. And so this derivative is actually just minus 1. And so what we're left with, and since you can take a peek here, lambda 1, you can actually rewrite this whole thing as the derivative, the natural log of omega 1 with respect to E1, right? Because you get the 1 over that I'm going to divide by through by here, and then this is equal to the derivative of the natural log of lambda 2 with respect to E2. Okay, so this is actually our equilibrium state. And so again, we've sort of taken a look at the total number of ways the system can be configured based on the energy. But again, you could have, again, you really need to think like Avogadro's number, 10 to 23, and you could have this energy state be all held in one molecule and the rest are doing nothing, or any of these different combinations of the above. The important part is that there's some distribution of that. And right, the total number of states, the total number of unique states that this can carry is actually what we're talking about here with this omega. And the equilibrium is when changing with respect to E1 is equal to 0. It's actually, this is our equilibrium state. And so taking this whole thing, we will then actually define entropy to be Boltzmann's constant times the natural log of this thing. So this is going to be our definition of entropy. This is where it comes from, and so that's why you will hear people talk about entropy being the disorder, or entropy being the total number of combinations a system could be put into. It's all the right kind of flavor. It's all the right kind of flavor. And then, so if I sneak a K in here, what you're going to find is that this all happens, let's go back to our macro state. These two systems are going to exchange heat, right? They exchange energy until their temperature is balanced. And so actually what we've done here is that this is ds dE, so I'm going to put that K back into here. That is equal to 1 over temperature. Okay? So the partial derivative of entropy with respect to energy is 1 over temperature, or sometimes you may see it otherwise as dE ds is equal to temperature. Okay? And so that is really the first root of thermodynamics by having to go down into these microstates and take a look at it. And then honestly, the way we then will build up the rest of thermodynamics is kind of from here. And so if I think of differential in energy, I can take the partial of that energy with respect to entropy, ds. I can take the partial of energy with respect to the volume, because remember that's one of my macrostates, d volume. And I can take partial of energy with respect to n here, dn. And in the end, this is our thermodynamics. That means dE is equal to temperature ds. This whole thing will show that it is pressure, so minus P dV. And then this is our chemical potential, mu dN. And that is the fundamental equation of thermodynamics. And I hope you can now recognize at least this thing right here as that Q. That is the thing that we have been unable to sort of get as humans. It came off the board here a little bit. So right here, Q is equal to the integral of T ds. So that the way we can finally describe heat is the temperature and the change in entropy. This, of course, is none other than our work, and then that's our chemical reactions and things like that. That's thermodynamics. And so we're going to stay in the statistical mechanics just for a few more lectures, if you will, to pull out a little bit more out of this. And so, dear reader, read through that book. Again, I would caution you, you don't have to dig all the way down into the full counting of what they would do from here's this quantum state and microstate. If you've had some quantum physics, it's okay. Don't feel afraid to go do it. But really, where it starts is at, my funny example here of 2 and 4 molecules, like this is the joke. It's like usually like 10 to the 23, 10 to the 24, right? Avogadro's number. This whole thing has this crazy amount of statistics, and that's why some of this works. Okay, but ultimately, the key concept here was, as you merge these two, it's actually a multiplication. Because it's a multiplication, we can take a look at the energy. We know the total energy is this. So we're able to find the equilibrium state, which is honestly the configuration under which this doesn't change, for which the total configuration, the total possible ways you can set up a system isn't changing. That's equilibrium. We then walk through that and find a relationship between effectively the natural logs of the number of those systems. We throw K in there for units, and we call that thing entropy. And then we're actually left here now with this beautiful thing. So we have now a sense of entropy. We actually have a sense of temperature. Both of those things are actually better defined here down in the microstate, and then we've landed on our pure thermodynamic equation. So we'll see you next time.